Hello, today we are diving into a crucial topic in AP statistics, the sampling distribution for the difference between sample proportions. By the end of this lesson, you will be able to calculate the mean and standard deviation for the difference between two proportions, justify the conditions needed to use a normal model, and interpret these values in a real-world context. If you have ever wondered if a higher proportion of seniors at your school like coffee compared to freshmen, or if a new medication works better than an old one, you are looking at the difference between two sample proportions. Let's get started. In this scene, our goal is to define the parameters and statistics for two independent populations. Imagine we have two distinct populations. Let's call the first one population 1. It has a true population proportion, which we label as P1. When we take a sample of size N1 from this population, we calculate a sample proportion, P hat1. Similarly, for population 2, we have a true proportion P2. We take a sample of size N2 and find the sample proportion P hat 2. The focus of this lesson is the behavior of the difference between these two sample proportions, P hat 1 minus P hat 2. If we took every possible pair of samples from these two populations and subtracted their proportions, the resulting values would form what we call the sampling distribution for the difference between sample proportions. Understanding the center, spread, and shape of this distribution is what allows us to make statistical inferences. Our first learning goal is to calculate the center and spread of this distribution. Specifically, we need to know the mean and standard deviation of the sampling distribution of P hat 1 minus P hat 2. The mean of this sampling distribution is the simplest part. It is exactly what you would intuitively expect. The mean, or expected value, of the difference in sample proportions is simply the difference in the true population proportions, P1 minus P2. This tells us that the difference in sample proportions is an unbiased estimator of the difference in population proportions. Now, for the spread. The standard deviation formula looks a bit more complex, but it follows the rules of combining variances. To find the standard deviation, we take the square root of the sum of the variances of each individual sample proportion. Remember that the variance of a single sample proportion is P times 1 minus P, divided by N. Since we are dealing with independent populations, we add those variances together and then take the square root. Notice that even though we are subtracting the proportions to find the mean, we add the variances. This is because combining two random variables always increases the total variability. Before we move forward, we must ensure the mathematical models we use are actually valid. In statistics, we don't just plug and chug. We must justify that our data meets specific conditions. These conditions allow us to use the formulas we just discussed, and eventually use the normal distribution. The first is the randomization condition. The data should be collected using two independent random samples. If the data comes from an experiment, the treatments must be randomly assigned to the experimental units. This ensures that our samples are representative and that the two groups are independent of each other. Next is the 10% condition. This is only necessary when we are sampling without replacement from a finite population. The size of each sample, N1 and N2, must be less than or equal to 10% of their respective population sizes, capital N1 and capital N2. This allows us to assume the trials are virtually independent, even though we aren't putting subjects back into the pool. Finally, to assume the sampling distribution is approximately normal, we check the large counts condition. We need the expected number of successes and failures in both samples to be at least 10. That's 4 separate checks. If all 4 are met, the sampling distribution of P hat 1 minus P hat 2 will be approximately normal. Let's apply these concepts to a practical scenario. This will help us hit our third objective, interpreting these values in context. Suppose that at a very large university, 70% of teachers drink coffee daily, while only 45% of students do. A researcher takes a random sample of 50 teachers and a separate random sample of 60 students. We want to describe the sampling distribution of the difference in the proportion of coffee drinkers, P hat teachers minus P hat students. First, we must justify the conditions. The problem states both samples are random. We also assume the groups are independent of one another. Since it is a very large university, 50 teachers is certainly less than 10% of all teachers, and 60 students is less than 10% of all students. For the large counts condition, we calculate the expected successes and failures for both. For teachers, we expect 35 successes and 15 failures. For students, we expect 27 successes and 33 failures. Since all 4 values are greater than or equal to 10, we can conclude that the sampling distribution is approximately normal. Checking these conditions is a mandatory step in any AP statistics free response question. Now that we have verified our conditions, let's calculate the specific parameters for the coffee example. First, we find the mean of the sampling distribution. The mean is simply 0.70 minus 0.45, which equals 0.25. In context, this means that if we took many samples of 50 teachers and 60 students, the average difference in the proportion of coffee drinkers between those groups would be 25 percentage points. Next, we calculate the standard deviation using our formula. We plug in the values for teachers, 0.7 times 0.3 divided by 50. Then we add the values for students, 0.45 times 0.55 divided by 60. Doing the math, we get the square root of 0.008325. This gives us a standard deviation of approximately 0.0912. This tells us the typical amount that our sample difference will vary from the true difference of 0.25. Understanding this variability is key to determining if a sample result is surprising or totally normal. Since we confirmed the large counts condition and calculated the mean and standard deviation, we can now visualize the entire distribution using the normal model. Because all conditions were met, the sampling distribution of the difference in proportions of coffee drinkers, teachers minus students, follows an approximately normal curve centered at 0.25. Using our standard deviation of approximately 0.0912, we can mark the scale. One standard deviation above the mean is 0.3412, and one standard deviation below is 0.1588. Now, let's think about a specific probability. What is the chance that, in our samples, a higher proportion of students drink coffee than teachers? That would mean our difference, teachers minus students, is less than 0. Looking at our graph, 0 is more than 2 standard deviations below the mean. We can calculate a z-score to find this exactly. 0 minus 0.25 divided by our standard deviation of 0.0912 gives us a z-score of approximately negative 2.74. The probability of getting a z-score this low is about 0.0031. This tells us it would be extremely rare, less than a 1% chance, to find a sample where more students drink coffee than teachers, given the population parameters we started with. This is the power of sampling distributions. They tell us how likely our sample results are. Let's try a second example to solidify these skills, this time focusing on an experiment rather than a survey. Suppose a pharmaceutical company is testing a new headache medication. In the population of all headache sufferers, the true success rate for the new drug is 80%, while the old drug has a success rate of 70%. In an experiment, 200 volunteers are randomly assigned to 2 groups of 100 each. We want to find the probability that the sample proportion for the new drug is at least 15 percentage points higher than the sample proportion for the old drug. This is a probability question about the difference between 2 sample proportions. Before we calculate anything, we must justify our conditions. Since this is an experiment, we don't need the 10% condition for independence. We only need to verify that treatments were randomly assigned to the experimental units. The problem states they were, so the randomization condition is met. Next, we check for normality using the large counts condition. For the new drug, we expect 80 successes and 20 failures. For the old drug, we expect 70 successes and 30 failures. All 4 values are at least 10, so the sampling distribution of the difference in proportions is approximately normal. Now that we've cleared the conditions for our headache medication experiment, let's find the parameters of this specific sampling distribution. We start with the mean. The mean of the sampling distribution is 0.80 minus 0.70, which equals 0.10. This tells us the center of our normal model. We expect the new drug to have a sample success rate 10 percentage points higher than the old drug on average. Now, let's determine the spread using the standard deviation formula. Next, we look at the standard deviation. We plug in our values, 0.8 times 0.2 over 100 for the new drug, and 0.7 times 0.3 over 100 for the old drug. Adding these variances gives us 0.0037. Taking the square root, we find a standard deviation of approximately 0.0608. The typical difference between the sample proportions will vary by about 0.0608 from the true difference of 0.10. With a mean of 0.10 and a standard deviation of 0.0608, we are ready to calculate the probability of seeing a difference of at least 15%. Now we can solve for the specific probability. What is the likelihood that our sample shows the new drug performing at least 15 percentage points better than the old one? We are looking for the area under our normal curve to the right of 0.15. Let's visualize this. Our curve is centered at the true difference of 0.10. we want to find how far 0.15 is from that center. We calculate the z-score by taking our observed difference of 0.15, subtracting the mean of 0.10, and dividing by our standard deviation of 0.0608. This gives us a z-score of approximately 0.82. This means a 15% difference is less than one standard deviation away from the mean. It is a fairly common occurrence. Using a standard normal table or a calculator, we find the area to the right of 0.82. The probability is approximately 0.2061. In context, this means that even though the new drug is only 10% better in reality, we will see it perform at least 15% better in our samples about 20% of the time just due to random chance in the sampling or assignment process. At this point, you might be wondering why we use such specific formulas and conditions. Let's take a moment to reflect on the logic behind combining these two proportions. A common mistake is to subtract the variances because we are subtracting the proportions. However, remember the rule for independent random variables. When you combine two variables, whether you add them or subtract them, the total uncertainty or variance always increases. Think of it this way: more samples mean more sources of variation. Imagine you are measuring the height difference between two people. If your measurement for the first person is slightly off, and your measurement for the second person is also slightly off, the error in the difference could be even larger. This is why we add the variances before taking the square root to find the standard deviation. Think of the conditions as a checklist for quality control. Randomness ensures our mean is centered at the right spot. The 10% rule ensures that our standard deviation formula isn't overestimating the spread, and the large counts condition ensures that the pile of data actually looks like a bell curve. What if conditions aren't met? If the large counts condition fails, say if one of your expected counts is only 5, the distribution might be skewed or have gaps. In that case, using the normal model would give you an inaccurate probability. Always double-check those counts. Take a moment to think. If we doubled our sample sizes, what would happen to the standard deviation of the difference? Since the sample sizes are in the denominator, increasing them would make the denominator larger, which makes the overall standard deviation smaller. This means larger samples give us a more precise estimate of the true difference. Let's tackle one more comprehensive example to make sure we've mastered all three learning objectives: calculating parameters, justifying conditions, and interpreting in context. Suppose 60% of city residents shop online at least once a week, compared to 50% of rural residents. A researcher takes a random sample of 80 city residents and a separate random sample of 80 rural residents. What is the probability that the city sample proportion is less than or equal to the rural sample proportion? This question is asking for the probability that our sample results show no difference, or even a difference in the opposite direction of what we expect. The samples are stated to be random. We can assume city and rural residents are independent groups. In any reasonably sized region, 80 people is less than 10% of the total population of city or rural dwellers. All four values, 48, 32, 40, and 40, are greater than or equal to 10. Therefore, the sampling distribution is approximately normal. Because the conditions are met, we can use the normal distribution. The mean difference is 0.10. Our standard deviation is approximately 0.0783. Here is the sampling distribution centered at 0.10. Calculating the z-score, we find it is approximately -1.28. There is about a 10% chance that a sample of this size would fail to show the city having a higher online shopping proportion, simply due to sampling variability. We have now successfully applied every skill from this topic. To wrap up our exploration of Topic 3.9, let's review the critical connections we've made today. Understanding the sampling distribution of the difference between two proportions is the bridge between simple probability and the powerful inferential tests you will perform later in this course. First, we establish the parameters. The mean is simply the difference of the individual population proportions, confirming that our estimator is unbiased. The standard deviation formula reinforces the idea that variation accumulates. We always add the variances of our two independent samples. Second, we mastered the justifications. Without meeting these conditions, our calculations lack a solid foundation. Remember that the large counts condition is what specifically grants us permission to use the normal distribution curve for our probability calculations. Finally, we practiced interpretation. Whenever you describe a sampling distribution, be sure to use clear language. The mean is what happens on average across many samples, and the standard deviation is the typical distance a single sample's difference will fall from that mean. Think about it. How would the standard deviation change if we quadrupled both sample sizes? Since n is in the denominator under a square root, quadrupling the sample size would actually cut the standard deviation in half. This is the law of large numbers in action. You are now fully equipped to calculate, justify, and interpret the difference between sample proportions. Keep practicing these multi-step problems, as they are a staple of the AP exam. Great job today!